All right, so we'll just start today's lesson. We're looking at relations and functions today. We're going to look at function notation and word problems. We're also going to look at interpreting graphs of functions. Before we start, let's do a quick recap from last class. Let's say we have a function f of x is equal to 8 minus 2x, and we need to evaluate, let's do f of negative 4. All right, so we're looking to calculate f of negative 4. So we're going to replace our x with the negative 4. So 8 minus 2 times negative 4 like that. Make sure to use those brackets when substituting. All right, so this becomes 8. Negative 2 times negative 4 becomes positive 8. So 8 plus 8, and that gives me an answer of 16. All right, let's take a look at another example here. And this time we are given a function g of t, and it's equal to 56 minus 3t. And what is the value of t if g of t is equal to 11? All right, so in this case, g of t is equal to 11. We need to solve for t. All right, so set this up. 11 is equal to 56 minus 3t. All right, so I'll start by, I can subtract 56 on both sides. So again, we're just solving for t here. So 56 and 56 is gone. Cancels out or becomes 0. And then 11 minus 56, that becomes negative 45 is equal to negative 3t. All right, I'm still trying to solve for t, so I have to get rid of this negative 3. So divide by negative 3 on both sides. That leaves me with 15. All right, so that was just a quick recap of function notation that we looked at last class. All right, so we're looking at this example. It is on page 477 in modules. It's lesson number 10. So we're looking at this function here. H of t is equal to negative 2t plus 12. And it starts off, a candle manufacturer found that their long-last candles melted according to this formula. H represents the height of the candle in centimeters, and T represents time in hours. So the first thing we're going to do is put this into your graphing calculators. Just use x instead of the t, so negative 2x plus 12, just like this, into your y equals, and then we will graph that, and it will look like this. Right, depending on what your window scale is. My window scale, my x is going up by 2, and my y is going up by 5. All right, so I'm just going to do a sketch of this graph. All right, so my y-intercept is going through at 12, and the x is going through at 6. So it looks like this. And this is our t, and this is h of t. All right, so our first question for this function is, what is the value of h of 5? All right, so h of 5, using our formula here, we just have to substitute that in. So h of 5 becomes negative 2 times 5 plus 12. All right, so negative 10 plus 12, this gives me an answer of 2. All right, so h of 5 is equal to 2, but what does that actually mean? So that means that the height of the candle is 2 centimeters after 5 hours. All right, so again, when we were looking at h of 5, this 5 here was representing our t for hours. So after 5 hours, we got an answer of 2. So 2 centimeters is the height of our candle after 5 hours. All right, next let's evaluate the following, and we'll also explain what they mean as well. So h of 0. All right, and what does that mean? So let's plug that into our equation. So negative 2 times 0 plus 12. And that gives me an answer of 12. So that means at time 0, the height of our candle is 12 centimeters. So the starting height of the candle is 12 centimeters. All right, next, h of 6. So let's look at h of 6. So negative 2 times 6 plus 12. So that gives me negative 12 plus 12, which is equal to 0. And what does that mean? So that means 0 centimeters at after 6 hours. So basically, after 6 hours, the candle has burned down to 0 centimeters. All right. And the last one here is what would happen if we had h of 8. So h of 8. All right, so after 8 hours, so let's take a look here. So negative 2 times 8 plus 12, that gives me an answer of negative 4. All right, so looking at our graph, looking at our graph here, we know that at 6 hours, our candle has burned down to 0. So if we go to 8 hours, it actually has no meaning. All right, so I'm just going to finish that here, and then I'll put that back for you. All right, so this means there's no meaning because we don't have a negative height for our candle. So we can just say here, no meaning. All right, so we'll just leave that here. I'll just pause it. All right, so the next question to this example on the candle is how long will it take for the candle to burn down to a height of 7 centimeters? So this time we're given the height of 7 centimeters and we have to solve for t, which is in hours. So 7 is equal to negative 2t plus 12. All right, and we need to solve for t. All right, so to solve for t then, I'll subtract 12 on both sides. That leaves me with 7 minus 12, which is negative 5, is equal to negative 2t. And then I'm just going to divide both sides by negative 2. All right, so t is equal to, and then I'm just going to put it into decimal form of 2.5. Okay, so 5 over 2 or -5 divided by -2, that gives me 2.5 hours. All right, so that's how long it will take for the candle to burn down to a height of 7 centimeters. All right, the last thing we have to do with this question is just figure out the domain and range. So I'm just going to put the graph up here one more time just to show the domain. Right, so when we look at this graph, again, time, we don't show negative, it doesn't have any meaning, negative time. So our domain is going to be from 0 to 6 hours. All right, so our domain we would write as t is going to be greater than or equal to 0 hours, but it's going to be less than or equal to 6 hours. And then t is the element of real numbers. And then our range here, when we look at our sketch of our graph, the highest point is 12 down to 0. So our height, maximum height is 12 down to 0. All right, so our height, or our function h of t, is going to be less than or equal to 12, but greater than or equal to 0. And it's the element of real numbers. All right, so we're just looking at this graph here. So our y-axis here is amount of fuel in liters, and our x-axis is time of the day. And what we can see here is that this graph has been divided into segments, 8 segments in total, so from A to B, B to C, C to D, and then D to E, E to F, F to G, G to H, and then H to I. All right, so what we're going to do is explain what is happening in each of those segments, basically. So let's just start with A to B, what is happening. So amount of fuel, so it's decreasing. Here, B to C, the fuel is staying at a steady rate here. Then time stays constant, and then there's an increase in fuel. So let's just write that down. So we'll start with A to B. All right, so this is the example. It's on lesson number 11, page 480. All right, so we're just looking at that graph and what is happening from A to B. A and B. All right, so from A and B, we saw that our fuel was decreasing, so that means the fuel was being used up, and it was 3 hours when we looked at that graph. So I'll just show that one more time here. So from A to B, so B is right there, so 1, 2, 3 hours. All right, so from A and B, we can say there's driving at a constant rate for 3 hours. All right, for B and C, that's when there's no change happening in the fuel. It's just kind of staying steady there. So most likely there's a break from driving, and it was 30 minutes when we look at the time. So we would say there was a 30-minute break. There's no driving happening because there's no fuel being used. All right, and then when we look at our next section here, we haven't moved, time hasn't moved, but we've gone up in fuel from C to D. So most likely there has been some refueling at the gas station. Okay, so filled up on gas. All right, next question is asking what is the rate of fuel consumption between D and E? So this is part B. So from D to E, what is our fuel consumption? So if we look at our graph from D to E, so we're going from D, 60 liters of fuel at D, all the way down to E, which is 25 liters of fuel. So we'll just we will subtract those two quantities. So 60 liters minus 25 liters gives us 35 liters. All right, but the question is asking for the rate of fuel consumption in liters per hour. So in how many hours did we use 35 liters? If we go back to our graph, here, from D, starting from here, so that's half an hour, and then 1 to 3 hours. So 3.5 hours from D to E. That is the time. Time is 3.5 liters. So now we can figure out our rate. So our rate would be 35 liters. Sorry, that's hours. 35 liters divided by 3.5 hours. And then just divide that. That gives us our rate of 10 liters per hour. All right, part C to this question is asking which line segment represents the car being refueled for the second time. So let's go back to our graph. And when are we refueling? So it has to be happening between here, so G to H is when we have refueling happening. So part C here would be GH. All right, calculate the total time when the car is being driven. All right, so to calculate when it's actually being driven, we have to ignore those breaks that were taken. So if we look at our graph here, there's two breaks taken here. There's a half-hour break taken right here, BC, and there's a 1 hour break taken here at EF, so 1 hour here and half an hour here. So our total time would be from 7 in the morning all the way to 5 here, and subtract out an hour and a half. All right, so a total of 10 hours. Subtract out that break of 1.5 hours, and that gives us a total of 8.5 hours of being driven. All right, and our last question here is if fuel costs 85 cents per liter, calculate the cost of the fuel used for the first day of the journey. So looking at the journey on this first day, so we know it's 85 cents per liter, and we're going to calculate the cost of the fuel for the first day. So we're going to calculate from A to B, that's when it was being driven, and then D to E, F to G, and then H to I. All right, so all we're going to use to figure out our cost is fuel used So from A to B, it's going to be 50 minus 20, which is 30. From D to E, it is 60 minus 25. From F to G, we are 25 minus 15. And then H to I, it is 60 minus 50. So I'll just write that out and we'll calculate fuel used. All right, so 50 minus 20, that was at AB. And then at DE, it was 60 minus 25. And then at FG, 25 minus 15. And then at HI, 60 minus 50. All right, so that gives us 30 plus 35 plus 10 plus 10. So when we add that up, we get 85 liters. All right, and we know that it's 85 cents per liter. So we'll take that 85, multiply by 85 cents. And that gives us a total of $72.25. All right, so we're just looking at two graphs here. They're both speed time graphs, all right? So our y-axis is speed, our x-axis is time for both of these graphs. They just look different. So let's go through something, a possible scenario that could be happening for the first graph here. All right, so from this point to this point, it's constant speed, traveling over a certain amount of time. So from here to here, we would just say a vehicle is traveling at a constant speed. All right, next from here to here, we see the speed is slowing down. So you could say something like the vehicle has come to a playground zone, or maybe a construction zone, or something else. Maybe there's an accident on the road. So the speed has decreased. All right, so at this decreased speed now from here to here, the car is now traveling at a constant speed, but through that zone, so at a decreased speed. All right, once that zone ends, the car or vehicle speeds up again, but not quite to how fast they were going originally. So they have sped up though. Then they're traveling at a constant speed for a certain amount of time. And then lastly, the speed is decreasing, but it decreases all the way to a stop. So you could say maybe this car has stopped at a stop sign, or maybe a red light, or maybe they've gotten to their destination. All right, when you see something like this, kind of curved like this, and it's steady, you could use an example like a pendulum swinging back and forth, maybe in like a grandfather clock or something like that. All right, the next examples here, sketching a graph. The first part here, sketch a graph with no scale, so you're not actually putting any numbers here. But what would be happening if the oven temperature, what would be happening in the following if the oven temperature, what's happening to the temperature when you're baking a pie? All right, so let's sketch a graph of what would be happening when you're baking a pie. All right, so this is the oven temperature, degrees Celsius, and this would be our time in minutes. All right, so whatever the temperature is, starting point of the oven, it's not going to be at 0. It would be something like room temperature. So your graph would look something like this, increasing to whatever you're baking at, maybe 350 degrees Celsius, and it's going to bake for a certain amount of time at that constant temperature, and then eventually the oven will turn off again and go back to its original temperature at whatever the temperature was of the oven, room temperature. The other example here is Ben is taking part in a 100-meter sprint. All right, and again, it is a speed time graph. So time in seconds and speed in meters per second. All right, so he would start at time 0. He would start at 0, increase in speed and constant speed for a certain amount of time, and then slows down and will come to a stop back to 0.